So the next 3 or 4 lectures will take a diversion from our discussions of chapter 9 of operational amplifiers, and we'll jump ahead to chapter 10, which is about stability and compensation. This is so that you will be ready to do assignment 4 in time. And I'm beginning this with a lecture on negative and positive feedback systems, some observations as I call it. Most of this is revision of what you've done in your undergraduate courses, but there are some observations that may be new. In any case, this sets the stage for our discussions on stability and compensation. So let us begin. So we'll look at this very simple unity gain feedback opamp circuit. So the input is applied to the positive terminal, the output is connected to the negative input. So this is a unity gain negative feedback, and let us study this for the next few minutes. So we write the equation. So we say for the operational amplifier, VO is equal to A into VI minus V minus, where V minus is the negative input terminal. Of course, in this circuit, V minus is equal to VO. So we say this, and we substitute, and then we solve for VO. So we'll get VO equal to AVI over 1 plus A. And if A is very large, then of course this is equal to VI. Now let's look at this qualitatively, the negative feedback of this system. So we say if VI increases, then because of the increase in VI and because it's connected to the positive terminal, VO increases. As VO increases and it is fed back to the negative input terminal, that causes this to increase, of course, and this increase causes VO to decrease because it is a negative input terminal. So the forward path and the feedback path are opposed to each other. One is causing VO to increase, another is causing VO to decrease, and this is what, of course, defines a negative feedback system. More generally, if the feedback factor was not 1, it is 1 here, if it was some beta, then you know that VO can be written as A over 1 plus A beta into VI. Alright. With this, let us study the frequency behavior and then the transient behavior of the same circuit, but now with the gain being a single pole transfer function. So we say A, which we've just put A here. Of course, it is always a function of frequency. So let us consider A to be a single pole transfer function and then substitute this to find the closed loop gain. And here omega 0 is the single pole frequency, and as you know, this is also the minus 3B bandwidth of the amplifier. So we say VO is A over 1 plus A, where A is A0 or 1 plus S2 over omega naught, 1 plus A beta, I'm sorry. And then we multiply and divide by 1 plus S by omega 0. So we'll get A0 in the numerator, 1 plus S by omega 0 here, plus A0 beta. So that is this. Then we take 1 plus A0 beta out and take it up. So we'll get A0 over 1 plus A0 beta divided by 1 plus S divided by omega 0 into 1 plus A0 beta. So this is again of the form sum A divided by 1 plus S by some omega. This of course is the low frequency closed loop gain A0 over A0 or 1 plus A0 beta, and this is the closed loop bandwidth. So I'm calling this A0 closed loop and omega closed loop. And so A0 closed loop is this, and omega closed loop is omega 0 into 1 plus A0 beta. And I'm also writing this multiplying and dividing by omega closed loop. So we can write this as omega closed loop divided by S plus omega L, because A0 closed loop is approximately 1. Alright, we'll come back to this in a minute. Let us discuss these two for a couple of slides. So, you know the definition of a unity gain bandwidth, right? Unity gain bandwidth is the frequency at which the uh, gain, the V over Vi, the magnitude becomes equal to 1. So, let us find this. So, this is our transfer function. This is the open loop transfer function. Uh, and for this, we say, well, when the magnitude is 1, a0 is 1 is equal to a0 by 1 plus j omega t. So when omega is omega t, the magnitude is 1. And we say, well, omega t is going to be much greater than omega 0, and therefore we can ignore the 1, and so we get this, and then the magnitude means j goes away and the omega 0 goes up, so we get a0 omega 0 by omega t. So omega t equal to a0 omega 0. You are familiar with this from undergraduate days. Stated in words, this is saying that the unity gain bandwidth of this transfer function is equal to the low frequency gain multiplied by the minus 3 dB bandwidth. It is a product of these two, and this is why the unity gain bandwidth is also often called the gain bandwidth product, or just GBW product. Now let us recognize that this omega t equal to GBW or A0 omega 0 is valid only for a single pole transfer function. If the transfer function had multiple poles in the denominator, then the unity gain frequency will be smaller than A0 omega 0. Alright, please prove this. It is not difficult, but it is important to show that omega t is less than A0 omega 0 if there are more than one poles. Alright, we will see that in the, well, after actually maybe 3 lectures or so, that for all stable systems, the single pole approximation of the transfer function is valid up to the unity gain frequency, and therefore any transfer function of an amplifier can be approximately written as this above the unity gain frequency, and therefore this omega t equal to a0 omega 0 is usually valid for all stable amplifier systems. We shall see this. This is not true for comparators because comparators are used only in open loop, and if you close the loop they will become unstable. Okay, let's talk about the closed loop bandwidth. So we wrote this, so let me go back and just refer. So this, we derived this for the closed loop. The transfer function is a0 closed loop by 1 plus s by omega cl, where a0 cl is this and omega cl is this. Alright, so let us look at this again. So we say the gain bandwidth product of the closed loop transfer function is a0 cl into omega cl, and we substitute for a0 cl and omega cl, and 1 plus a0 beta cancels, and so we get the closed loop gain bandwidth product, which is this, equal to a0 omega 0, which is the open loop gain bandwidth product. So we say that the closed loop gain bandwidth product and the open loop gain bandwidth product are equal, or in other words, as we apply negative feedback to an amplifier by putting a beta network, independent of the value of beta, the gain bandwidth product remains constant because the 1 plus a0 beta cancels. Alright, this is what you learned in your undergraduate. What you learned is that the gain bandwidth product of an amplifier remains constant. The implication of that statement, or the more complete statement, is that the gain bandwidth product of an amplifier remains constant when negative feedback is applied to it and the feedback factor is varied. Alright, it is very important to add this condition. The gain bandwidth product of any amplifier does not remain constant. In fact, in this course, we are designing the internals of amplifiers. For us, the gain bandwidth product on an amplifier is not constant. We are actually designing it. Once we've designed it and created an operational amplifier, and we keep the internal circuit of the operational amplifier unchanged, we fix it, and then we apply negative feedback to it. Then, keeping the internal circuit of the op-amp the same, when we apply negative feedback, the gain bandwidth product does not change even when we change the feedback factor. Alright, it's a very important thing to remember. It is not emphasized a lot in undergraduate discussions. Okay, now let's go back to our negative feedback, the VO equal to omega CL by S plus. Okay, let me go back and show that again. So we derived this. VO is equal to A0 by 1 plus S omega CL, and we say A0 CL is 1, and the omega CL goes up, so omega CL by S plus omega CL. Alright, so this is the closed loop VO for our unity gain feedback operational amplifier. Now let us find the transient response. So we say for this amplifier, suppose I apply a unit step at the input, I want to see what happens to the output. So in the Laplace domain, a unit step at the input is Vs over S, where Vs is the magnitude of the step. So Vs times a unit step is what we are applying. So we say Vi is equal to Vs over S. And now I want to find the transient response, which means I want to find how VO behaves as a function of time. So we take the inverse Laplace transform of this, and you've done this inverse Laplace transforms. The way what we'll do is we'll do partial fractions of this. So VO is, we'll take Vs out, and the partial fraction is 1 by S minus 1 by S plus omega CL, the two first order terms in the denominator. So this will be S plus omega CL minus S in the numerator, which is omega CL, which is this. So this is our partial fractioned Laplace transform. We take the inverse transform. VOT will be Vs. 1 by S is just 1. 1 by S plus omega CL, the inverse Laplace transform is e raised to minus omega CL t. And there is a minus here. Alright, so this we are familiar with. We started with a single pole transfer function. We apply a unit step to a single pole transfer function. We'll get an exponential decaying output voltage as a function of time. Right, so if we were to, just for the sake of completeness, we plot it at t equal to 0, VO is 0, and it goes exponentially e raised to minus omega CLT, and as t tends to infinity, this term goes away, and if Vs is equal to 1 volt, the output will approach 1 volt exponentially. Alright. Now, of course, a single pole transfer function indicates that the circuit has a single energy storage element, and we know that single energy storage elements will have a single exponential in the transient response. Alright. Now, let us discuss the same thing for positive feedback. So, we take the same circuit, but now I have reversed the terminals. So, we are connecting the output to the positive input of the operational amplifier, and we are applying an input to the negative terminal. Alright, now the question we are asking is, suppose Vi is, let us say, 1 volt, or let's say a unit step is applied at the input. Now let us start with just a DC 1 volt. Suppose I have applied a DC 1 volt to Vi, what will be VO? Can you please answer the question? And once you answer it, see if you can prove your answer, whatever answer. Mathematically, can you prove the answer? Alright, please pause. This is a very nice exercise for you to think about before you see the answer in the subsequent slides. So please pause, think, spend some time thinking, and especially about proving the answer mathematically. Okay. Alright, let's write equations. We'll first write equations for DC, and then we'll do the transient. So we say VO is equal to V plus minus V minus, which is VO minus VI. V plus is equal to VO, So we get VO equal to AVO minus VI. We take the AVO on the other side. When we solve for VO, we'll get VO equal to minus AVI divided by 1 minus A. And if A is much greater than 1, then we ignore the 1, then the minus A cancel, and we are getting VO is approximately equal to VI. Alright, even for this circuit, VO is approximately equal to VI. I think you know that this is not correct, and we'll see mathematically now. Qualitatively, let us say we apply some input, and let's say it increases. If Vi increases, because this is negative, VO will decrease. If VO decreases, that is fed back to the positive terminal. So this decreases VO further because this is connected to the positive terminal. So both the input as well as the fed back paths are causing VO to decrease. Both have the same trend, and of course this is what defines positive feedback. This circuit has positive feedback. So if you are to take this further, we'll say that, well, VO will keep on decreasing until something happens, which let us see what happens. So let us do a transient analysis. Okay, so we say A is, again we'll take a single pole transfer function for A 0 over 1 plus S over omega 0. Then for the closed loop, VO is minus A by 1 minus A, and we substitute, then we take the 1 plus S by omega 0 down, so we'll get minus A by 1 plus S by omega 0 minus A0. And then we'll take the 1 minus A0 out, so we'll get minus A0 by 1 minus A0 divided by 1 plus S by omega 0 into 1 minus A0. Alright, now I'm taking the negative signs inside, so we'll get A0 by A0 minus 1, and this negative outside, so we'll get A0 by A0 minus 1, 1 minus S by omega 0 into A0 minus 1. A0 is of course much greater than 1, so now this number is positive and this number is also positive, and there is a negative sign outside. And now again I'll so we say A0 CL, which is A0 by A0 minus 1, and omega CL, which is omega 0 into A0 minus 1. Alright, and then I'm taking omega 0 CL up and down, so we'll get omega, okay, so omega CL minus S, and I'm making it S minus omega CL, and then there is a minus up, omega CL, and A0 CL is approximately 1, so we can make this 1, and omega CL is approximately omega 0 A0. The magnitude of the bandwidth is the same as for the negative feedback, so we'll get whatever we'll get here. Now we apply, so we'll get minus omega CL by S minus omega CL, this becomes 1. And now we apply an input, a voltage step, so that Vi is Vs by S. Alright, so we apply Vs by S, so this is Vs by S. Now again we want to find the inverse Laplace. So we'll take partial fraction, so minus A0 CL Vs goes out, and we'll get 1 by S minus omega CL minus 1 by S. So that is, what is this? S minus S plus omega CL. So omega CL by S minus omega CL into S. Okay, so this is okay. Now we take the inverse Laplace transform. This stays as it is, 1 by S minus omega CL. Alright, the minus is what is critical. Remember, in the negative feedback, this was plus. In the positive feedback, this is minus. If this is minus, the exponential is plus. So this is e raised to omega CLT minus 1. Alright. So Vs, okay, so one small comment, VO is negative if Vs is positive. Okay, that's because if the input is applied at the negative input, so if Vs is positive, VO will be negative. But that is minor. The major is that VO is increasing exponentially as a function of time. Alright, this is a property of positive feedback. output increases exponentially with time, e raised to plus omega CLT. Alright, so if you were to plot it for some value of Vs, for some value of omega CL and Vs, we see that the output voltage of such as unity gain positive feedback amplifier simply keeps increasing. Here I have shown it up to 50 volts. Of course, it will keep on increasing to thousands of volts. Alright, with a negative input, so the output is positive. Alright, what happens in a real circuit? If I connect this circuit in the lab, which is trivial to do, just take any op-amp, put and connect the output to the positive input, apply some input step at the negative input and watch the output. What will we see? Will we see the output increasing exponentially with time forever and ever, 50 volts, 100 volts? Of course we won't, right? We won't see a voltage increasing for such large values. The answer is, of course, something to think about. But anyway, I'm continuing. In real circuits, the output voltage will increase exponentially with time until the voltage approaches VDD. VDD is the power supply applied to the op-amp. As the output voltage approaches VDD, we look inside the op-amp, the circuit inside the op-amp. Some transistors will go into triode, others will turn off, and the output will saturate at VDD. So in a real circuit with positive feedback, if we apply a voltage step at the input and watch the output, we'll see that initially it increases exponentially, but then it saturates to VDD and stays constant at VDD. Alright, let's look at an example. So we'll just take a simple differential amplifier and we've connected the output to the positive input of the let's treat this as an amplifier. So if this is the output, then this is a negative input, this is the positive input. So we've connected the output to the positive input, and let's say we apply a voltage step. Alright, so what will happen is when we apply a voltage step, the output, which is of course equal to the gate voltage of M2, will start increasing exponentially with time. Alright, now as it increases, the gate voltage of M2 will go higher than the gate voltage of M1, and as it rises higher and higher, more current from M5 is diverted to M2. Eventually M1 turns off. As M1 turns off, the current becomes 0. M3 is on because it has a DC bias at the gate, but no current through it. Therefore, the output becomes equal to VDD, 3 volts. Right? So this is what happens. So what is happening is that, so let's say initially both these are equal just for the sake of argument, and at some time equal to 0 when this is applied. And as this starts increasing due to positive feedback, VO1 starts increasing and M3 goes into triode, M1 turns off slowly, slowly, fast, whatever, as a function of time. And when M3 enters triode and eventually carries 0 current, the voltage gain of the differential amplifier becomes smaller and smaller and smaller. Right? The voltage gain was high when both the inputs are equal. The voltage gain becomes smaller and smaller and becomes 0 once the output saturates. So the equation, alright, so let's go back to the DC. So when we derived these, so this is the DC equations we wrote, and we say, well, VO is equal to VI. For deriving this, there was an assumption that, there were two assumptions actually. One was that the circuit had reached a DC steady state, and the second was that in the DC steady state, the amplifier had a high gain A. Alright. Now in an actual circuit with positive feedback, because of saturation, the gain becomes smaller and smaller and it no longer is high, and therefore these equations themselves become invalid. The circuit reaches DC steady state only with the gain becoming practically, well, very small or zero. All right. So one cannot apply DC analysis to systems with positive feedback of this type, DC analysis, assuming a high voltage gain or assuming that this equation is valid, right? Cannot be applied. All right. And because we made that assumption, we got the wrong answer, and this analysis was incorrect because of that assumption. All right, so that is this lecture. Next lecture, we'll talk about the stability of amplifiers.